In third period, we actually did a quick calculation of the escape velocity from Earth. And just so you guys are aware, when you actually look at what the escape velocity is, first we know this is the gravitational potential energy and it's negative. The idea here is that if you are on a planet and you give an object kinetic energy, and you want that object to reach the place where it will have zero energy, that threshold where we know the Earth no longer acts on it, then the sum of the kinetic energy plus the potential energy has to equal zero. So essentially, you're doing the work necessary to lift the object out of this gravity well. But ultimately, it's going to be 1/2 mv squared equals m1 m2 g over r. In this case, r would be the radius of the planet. Now, the m here represents the mass of the object, not necessarily the mass of the planet. So the escape velocity ends up being the square root of mg over r. And for us, it was like 11,000, about 11,200 meters per second from the Earth. Just to put that in perspective, it's about 4,000 meters per second to put something into a low Earth orbit. So the difference here between getting something to the escape velocity and getting something to orbit is a big difference. And be aware, we're not talking energy, this is velocity. Now, consider energy for just a minute, since in both cases, we tend to give these objects energy by burning fuel. And the fuel has a fixed amount of energy per cubic meter. Then when you compare these two velocities, consider this velocity is about 3 times greater than this velocity. And since the velocity is squared in the kinetic energy equation, then we're talking about 9 times more energy, or 9 times the amount of fuel. And you have to combust that fuel in about the first 11 minutes. Look, just to be honest, you can't build a rocket that big. And the biggest rocket we ever built was a Saturn V. And it was a rocket designed to take things not to the escape velocity. When you think about it, they only had to get it far enough away so that it fell into the gravity well of the moon, which is about 2/3 of the way to the moon. So that's not even near the escape velocity. And I do want to point out that this number is pretty fake. It's fake for a number of reasons, but the most important being, we assume that the Earth is by itself here, in the middle of a void with no other objects near it. But the Earth is trapped in the sun's gravity well. So the moment you escape the Earth, you still have not escaped the sun. And there's other objects there that also have their own gravity well. Now, most of the planets are pretty small and pretty far away from the Earth, but Jupiter is big enough to create a gravity well that would influence these objects. Look, we've not sent something easily out of the solar system. So talking about the escape velocity of the Earth isn't enough to get something to leave. To get something to leave, you have to take into account the whole solar system. 2 objects have done it successfully. The Voyager 1 and Voyager 2 space probes, which were launched back in the 70s, have been out there for almost 50 years. But we didn't give them enough energy when they were launched. We had to do some tricks to give them energy along the way, slingshotting them around planets, to use the gravity assist of those orbits to try and boost the kinetic energy of those probes. Now they have left the solar system. Yeah, 2 is sitting right in there. Don't you see it? I see the 2 right there. All right, good. I'm glad we don't have that problem. Let's talk about something else for a minute. This is the last piece. And this one is, I'll say that this is an easier piece to understand, but maybe not. I will tell you that when we get into second semester and we start having a better understanding of angular momentum, we're going to come back to orbits again because orbits conserve angular momentum. But orbits, as you probably can imagine, have to conserve energy. Once an object's in orbit, there's no external force in the system to add or take away energy unless the object itself propels itself or fires a motor or does something to its energy. There's no other forces out there. Gravity's conservative force, so the object and planet system will conserve mechanical energy. What this means is that as an object's in orbit, the combination of its kinetic energy and its potential energy will have to be a constant. Now, in a circular orbit, that shouldn't be a surprise, because in a circular orbit, the object is always the same distance away, so we know its potential energy isn't changing, and it has a constant velocity, so we know its kinetic energy isn't changing. That's not particularly interesting. On the other hand, now coming back to this, I would generally expect you guys to figure this out on your own, but that hasn't met my expectation in recent weeks. So I'd like to take a look at this for a minute. We know from what we've already talked about so far this year that this combination, 1/2 mv squared plus m planet g over the orbital radius, this would have to be the total energy of this object in orbit. However, it shouldn't be lost on you that we can figure out what this velocity is. In a circular orbit, we know the net force equals MAC. Right? It's in a circular orbit. We spent all that time figuring out the velocity of orbits. So if it's in this orbit, we know mp(g) over r squared has to equal mv squared over r. All right, we've been down this road a number of times. Now, I'm not actually going to solve for v. Cancel out one of the r's here, and I'll write this as mp(g) over 2r equals 1/2 mv squared. The amount of kinetic energy you must have to be in a stable circular orbit. This would be true for any circular orbit. That this represents the kinetic energy in that orbit. So, if I come back up here to the top, I can replace the expression I had for kinetic energy with a new expression that's in the same terms as the potential energy. And considering that I can get pretty easy common denominators here, I can express the total energy all in terms of the planet, the object, and the orbital radius. I'll get negative m mass of planet g over 2r as the total energy for any circular orbit. Now, these are consequences of applying circular motion to an orbit. Now, keep this in mind. You can figure out how much potential energy you have on the surface of a planet. And you can then figure out how much total energy is necessary to be in orbit. This is how you figure out the fuel requirements to send an object into orbit. You get a benefit that you're going away, that the potential energy is going to change and go down. But you're also going to have to acquire quite a bit of kinetic energy. Now, I would love to say that's as easy as it is, but you can probably expect that it's not. There's a lot of air resistance there to get you out into orbit, and well, that air resistance is probably going to take away quite a bit of this energy. Energy is not conserved going from here to here. Work done by friction. Not to mention the fact that you can only go so fast through the atmosphere before your ship self-destructs. So you have to decide how fast you wish to accelerate. This is why most of the time in lower orbits, the velocity of the spacecraft is kept artificially low. This is to protect usually the cargo or the occupants. And then as they get to the thinner parts of the atmosphere, they open up the throttle a bit and start to really accelerate. It's to keep the spacecraft from having generally catastrophic vibrations that destroy it. All right, that's all I want to talk about with orbits. You should expect that question or 3 on the multiple choice dealing with orbits, and this is the kind of stuff you should expect. There will not be an FRQ on your next test about this. We'll save those FRQs for second semester. All right? Any questions at all to this point? Okay. 4 big takeaways. Gravitational potential energy is negative because our reference is taken at infinity. The escape velocity comes from the amount of kinetic energy required to get you to a point where the force is 0. It comes from setting the kinetic energy equal to the potential energy. Energy in orbits is conserved. So the sum of the potential energy plus the kinetic energy remains a constant, even in elliptical orbits. In circular orbits, you can use centripetal acceleration to get a reduced answer for the energy of your orbit. However, your energies are going to be negative. When it comes to elliptical orbits, well, in elliptical orbits, the planet's constantly changing its distance away from the star. So R is always different. And also its velocity is always changing. You can probably imagine that the planet's going slower here than it is there. But since there's no external force in the system, the combination of the potential and the kinetic energy has to be the same everywhere. And has to be negative, because we're still trapped in this gravity well. Which means the potential energy will be a larger negative number than the kinetic energy is. So these are all still negative energies. But it's because of our reference for the potential energy. Now, this allows us to figure out how fast a planet must be traveling at different points, as long as we know one point. We can always figure out the others. It's a very cumbersome way to figure it out, though, which is why we tend to use other things, and we'll show that angular momentum is conserved next semester, and we'll probably use angular momentum because it's much easier. But just understanding now that the energy is conserved is something that you could be tested on. Depends on who it is. I still don't think you're jumping down the well to join your idiot friend. Now, you're both stuck in the well. It seems a little ridiculous, but perhaps it's more important to you to provide comfort than to get them out of the well. Now, just so you know, there's a bunch of you who probably should be trapped at the bottom of a well. Just so you know. I'm sure that we can probably think of a few people. No. But I might try and get you help. I don't know that I would help you myself, but I might get you help. Now, consider this. If you look at the problem from the standpoint that the ground is zero, then the person who might be, let's say 20 meters beneath you would have energy equivalent to mg times negative 20. They would have a negative amount of potential energy. They are trapped in the well. The well is negative. They would prefer to be out of the well, but there's no way for them to get out of the well without doing enough work to lift their body out of the well and bring them to zero. But the amount of energies we're talking about here are no different. The work done lifting the person is positive, whether the bottom of the well is zero or the ground is zero. The amount of work done is positive. And we know that because you're pushing a force upwards and the object is going upwards. The fact that we set the ground at zero is because we can. Being trapped in a well is perhaps, unfortunate. And to get things out of that well require energy. Now look, we can set the reference level anywhere. For planets, we set the reference level at infinity because it makes sense to do so. The fact that the potential energy is negative isn't because energy is negative. Potential energy is always relative. It's always relative to a point that you decide as a fixed point to compare energies. So we have chosen infinity to be the comparative point for all conversations due to gravity because that's one place that all points would have in common. Other places wouldn't have that in common. So that's why that place is chosen. On the Earth, we choose common for our situation, which is why that reference level always shifts in our problems. But if you think about the concept of a well, it will serve you in considering that getting out of that well is just like lifting something out of an actual physical well. There are lots of potential wells out there. The electron is trapped in a potential well around the proton. To get it out requires a certain ionization energy. You AP chemistry experts, that is the amount of energy required to leave the electric potential well created in the quantum state of the electron. It's still a well. We consider there to be a nuclear well in the nucleus of the atom, the amount of energy required to escape the nuclear force that binds the atom together. That's considered negative energies. All the ionization energies are called positive when you take chemistry, but we consider the actual energy levels of the electrons to be negative. So it's 13.6 electron volts to get the electron off of a hydrogen atom, which means that the lowest energy level in a hydrogen atom is negative 13.6 EVs. That's its potential energy level. And it's negative because it's a well. To get the electron to escape requires the addition of that amount of energy. So all things in nature that are bound together are considered to have negative potentials. Escaping them, separating them, brings them to zero. All right, I'm kind of done with this discussion unless you guys have any follow-up questions. All right, I hate to do this because it's such an insult, well, to me, but we're going to switch into review for a few minutes for last year's information. Of course, for people who had no last year's information, this is all new information. All right, ready, the three of you? Now, some people have always wondered, rightly so, why there is this difference between impulse and work. For those of you who do remember impulse from last year, you know where this is going. But let's just throw up here on the board real quick our definition of work as the integral of f dot dx. Let's also consider the algebra version of this for a constant force. F delta x cosine theta. That we say work is done whenever a force is used to move an object. That's a net force, then we know that we've changed the object's kinetic energy. And I'm hoping you guys remember that we went through a whole derivation using motion equations to demonstrate how this can become 1/2 mv squared. Do you remember that earlier in the year? Well, if you don't, then you weren't paying attention, but I do, because I remember doing this with you guys. Let's start with the first principle. Right, an excellent first principle. The problem is that this is not actually a first principle. I've told you that it is, and we will continue to call it that. You know, we'll say that this is Newton's second law, but this is actually not the second law that Newton published. This is the way we teach it to you guys, especially in introductory physics classes, because we start these classes with kinematics. But Newton's book doesn't start with kinematics. Kinematics is a consequence of his rules, not the foundation. He starts with a much different idea in mind. Now, I have started the whole conversation this year with the idea that acceleration is important because change in motion is more important than motion. That is the whole crux of this statement. That if you want to change something's motion, you will have to apply a force, and forces only come in a couple of variations. So dealing with grabbing something, being able to manipulate it requires a force, which means you have to understand how forces work. When we talk about picking up a coffee cup, that's kind of a pedestrian idea. But if you're trying to grab a neutron, how do you do it? You can't touch it. You can't get close enough to it. It doesn't respond to the electric force or the magnetic force. So how do you grab hold of one and move it? So when it comes to really solving physics problems, there are reasons why we have these fundamental ideas. If I want to change its motion, I have to find a way to apply a force to it, which means finding a force that will affect it. That's why I spend so much time on that idea of intrinsic properties. The realness of physics is sometimes pretty tough and daunting. Now, we just talked about ionization energy of an electron. You still have to find a way to do work on the electron. How do you give it that energy? How do you push on it? These are real problems that we have now solved and have found ways to do so. Newton wasn't starting here. Newton was starting someplace else. So to make this easy for all of you to see, I'm going to pick a few things you already know, this being the more important one. Not a big deal, right? The definition of acceleration, even in an algebra format. Little distributive property. Vectors all around. Newton wasn't interested in inertia as mass. Newton was interested in momentum as inertia. Newton defined the concept of momentum as an object's inertia while moving. He recognized that inertia wasn't just about mass, that inertia was a combination of an object's mass and an object's velocity, that you could affect the inertia of an object by changing its velocity, by making it move. Look, if I put a 20-gram weight on my desk, it is not hard for any one of you to change its motion. You can pick it up and throw it, flick it with your finger, drop it to the floor. It's easy to change its motion. But if I fire a 20-gram bullet, it's a lot harder to change its motion. The fact that it has velocity changes how difficult it is to change its motion. That's because as things move, they become more difficult to change their motion. This concept is momentum. And Newton was really on to the bigger ideas about physics, that mass and velocity are connected together. And it changes the difficulty in moving an object when it starts to be moving. So, Newton's law, as stated by Newton's second law, is not ma, but that net force equals the rate of change of momentum. That's truly Newton's second law. In fact, because we're in a physics class, and one that uses calculus, this is actually now, before you walk out the door, keep in mind, lowercase p is a symbol used for momentum. Momentum is a vector quantity, so it has direction. Momentum is not energy. They share similar features, but they are not the same. To understand what an object is doing, you need both. All right.